Hello and welcome to the second lesson in our fifth unit, Sine Functions, in our grade 11 University College math class. So today's lesson starts with investigating the sine function, and we're going to do that by recapping the things that we tackled yesterday. So the first thing I'd like you to do, and I'll just scooch this up a little bit, is just to copy out or redo this table that we generated yesterday. So what we were looking at was inputting specific values for theta, and then observing what the output value, the y, was. And once we finished this table, we put it on a graph, and we were able to observe this unique pattern that is a periodic function, which means that it's repeating. And yeah, now would be a good time just to hit pause, redo the table. Again, you can type the values into your calculator and then redraw this graph. It's good practice. We're going to be doing a lot of time graphing in this unit, or spend a lot of time graphing in this unit. So now's the time to knock the rust off. So hit pause, give it a go, and come on back when you're done, and we'll continue down the lesson. Okay, hopefully you're back with all this finished. As we move the note up, I just want to point out the last thing that we did in yesterday's lesson was to determine that this is indeed a function because it passes the vertical line test. And tying this to earlier units, again, we're going to articulate what the domain and range are for this function. So the domain, as you recall, are all of the x values, or the independent variable, which in this case is actually theta, as you can see here. So it is we're articulating all of the values for theta that will be true for this particular function, sine of theta. So let's start by filling it out with some of our typical notation. So the set of all theta such that theta is an element. In this case, we're going to use real numbers. It's because this is a continuous line that we see up here in our graph. Because it's a continuous line, it will include all the little values, not just 0 and 30 and 60 and 90, but all the little ones in between as well. So that's why we'll call this the set of all theta such that theta is an element of real numbers. Now this is the part where in our set notation we would articulate any limits that we have. And because with our exploration of coterminal angles yesterday, we know that this pattern, this sort of waviness, will go on in both directions forever. So there are no limits to the domain of our sine function. Obviously, we're talking about theoretical sine functions here. We're not talking about necessarily like a real-world example, which might have a limit. But generally speaking, if it's not given a context, the domain is wide open for the sine function. The range, however, is a little bit different, so let's set that up as well. So we'll start that off by saying the set of all y such that y is an element of real numbers. Again, real numbers because it's a continuous line. Y is the variable we're articulating on our vertical axis. Now let's look at the limits on this thing. So what is the highest point that our graph is going to reach? Well, here we can see that it is, oh, that's not what I want. It is 1 is the highest point. And even if this thing repeats over time, it's never going to get higher than positive 1. On the flip side, you'll also notice that it doesn't ever go any lower than negative 1. So that articulates sort of our high and low values. If we were doing sort of a number line, we'd be looking at something like this, where we include 1 and negative 1, and we have all these values in between that make up our range. So let's articulate that using our set notation. So we have the set of all y such that y is an element of real numbers where negative 1 is less than or equal to y, which is less than or equal to 1. Again, just as a remembering how we did this, this is our low value, this is our high value, and we make sure that we've got the right inequality signs in here by considering each of those cases. Negative 1, y will be greater than or equal to negative 1 if you look at just this little piece here. And then the second piece is written in a more traditional way where y is less than or equal to positive 1. So that's how we articulate our range. We're going to move into some terminology now specific to this unit. Similar to the way that in a unit on quadratics, we'd be talking about parabolas and vertex and axis of symmetry. We have some terminology associated with sine functions. So we're going to go through these. I'm not going to spend time talking about all of them since some of them are more important than others. But I will say that knowing what a periodic function is probably a really good place to start. And a periodic function is something that repeats at regular intervals, and you can see that mirrored in this component here of the definition. Periodic means happening or appearing at regular intervals and having repeated cycles. That makes sense to us. I'll be using the word peak for the highest point on this graph, which again is also a maximum, and I'll be using the word trough to speak about the lowest point, which is also a minimum. This is a helpful one right here, and when we talk about the period of a graph, we're talking about the interval of the independent variable, which is the angle of rotation, but is also often time, needed for a repeating action to complete one cycle. And the one cycle is probably the most important part there. We're going to talk about that a little bit as we look at the graph, but the period is something that we're going to be using over the course of the whole unit. Cycle you can read, but it's not something I'll be using a lot. Equilibrium axis is probably the next most important piece of terminology that we're going to be using. And like the axis of symmetry, the equilibrium axis is the equation of the line. So we're going to be setting this up as a y equals something, as in the same way as the axis of symmetry was an x equals something. So it's the equation of the horizontal line halfway between the max and the min. So a horizontal line, that's sort of what we would dot it in between the maximum and the minimum, kind of the point around which this cycle is going to be repeating, its middle value, so to speak. So we can determine it by a formula. So we're going to set this up. Let me just change up my colors here. So we would say that the equilibrium axis is equal to, if you were to take the maximum value and the minimum value and add them together and divide by 2, that is going to give you your equilibrium axis. Again, very similar to the way that we were finding the axis of symmetry. So if we were going to have here, let's just set this up, if we were to have here a maximum value of a +1 and a minimum value of -1, if we were to then combine those two together, 1 plus -1 divided by 2, that would give us 0 over 2, which would equal 0. So the formula for the equilibrium axis then would be y equals 0, which makes sense. Visually, again, we can see that our dotted line here, I'll change up my colors. So this line that goes through sort of the middle, y equals 0, halfway between our maximum and minimum values. Visually we can see that. We've got like this little chunk here above, we've got this little chunk here below. They are equal in terms of area, so the equilibrium axis splits between them. And like the axis of symmetry, if you have the maximum and minimum values, you can also just kind of even eyeball it as well. You don't necessarily have to go through the act of figuring it out algebraically, although you're welcome to. Okay, another piece of terminology that we're going to need is the amplitude. Now the amplitude is the distance from the function's equilibrium axis to either, so distance from equilibrium axis to either the max or the min. So it's something that can be applied twice. So I'm going to go over to our little drawing here. Now they've drawn it in that spot. I like to draw it in right under the maximum. So this distance here from our equilibrium axis up to the maximum point, or this distance here, these will be the same from our equilibrium axis to our minimum point. That is going to be our amplitude. We can also figure this out algebraically, where we can say that the amplitude will be equal to our maximum value, subtract our minimum value, and divided by 2. So in this case, again, let's just imagine that our maximum value is going to be, +1. Our minimum value is going to be -1. So let's add those two together, or rather, let's subtract those two. So we have a +1 minus a -1. and that's all going to be over 2. So that will give us 1 plus 1 over 2. I'm demonstrating some bad form here. Scooch over this way, and that will be equal to 2 over 2, which equals 1. So our amplitude is 1, and that makes sense. If we were going from our equilibrium axis, which would be 0, all the way up to the highest point, it would have a distance of 1. Similarly here, from 0 to -1 has a distance of 1. Now I do want to point out that an amplitude, it doesn't necessarily have a positive or negative value. What it has is just a unit of measure, in the same way that you wouldn't have like a negative distance. An amplitude is a distance from the equilibrium axis to the max or the min. So don't necessarily worry about a sign here. It has no sign, and I guess no sign sort of by default indicates positive, but an amplitude, it doesn't have a positive or negative value. So there we go. That's some of the terminology that that we're going to be using over the course of the unit. I'm going to end our first part of this lesson here, and we're going to come back and we're going to work a few problems using that terminology. So I'll see you in part 2.